This is the illustration video for dense prediction with attentive feature aggregation. Dense prediction tasks are fundamental enablers for many computer vision applications. To pursue higher performance, it is popular to exploit the multi-scale representations to balance preserving spatial details from shallower features and maintaining relevant semantic context in deeper ones. One approach is to progressively downsample the layer resolution as in image classification networks, and then upsample the resolution by aggregating information from different layer scales with layer concatenations. Another challenge of dense prediction tasks is that fine details are better handled in higher resolutions but coarse information are better in lower resolutions. To overcome this, HMA proposes a hierarchical attention mechanism that only needs 2 scales during training but can utilize more scales during inference. Despite the feature aggregation has huge success on dense prediction tasks, the predominant aggregation operations are still linear and do not consider feature interactions or selections between different levels or scales. Thus, we propose attentive feature aggregation, AFA, as a nonlinear feature fusion operation to exploits both spatial and channel attention to compute weighted averages of the layer activations. We designed 2 types of AFA for different aggregation scenarios and both employ simple spatial and channel attention to model complex feature interactions and attend to different features. For the simple binary fusion, we compute spatial attention from shallower features and channel attention from the other. For multiple feature fusion, we perform hierarchical attentive fusion by progressively aggregating features from shallow to deep levels. AFA is flexible and can be applied to widely used segmentation models to fully utilize the previously unused aggregated multi-scale features. Due to higher connectivity of its nodes, the DLA network can benefit more from our improved feature aggregation scheme, and thus we use AFA DLA as our final model. The experimental results shows that AFA can improve each model performance with only small computational and parameter overhead. Using attention to fuse multi-scale predictions can alleviate the trade-off in performance on fine and coarse details in dense prediction tasks. But the repeated use of attention layers may lead to numerical instability or vanishing gradients and hindering the performance. Inspired by neural volume rendering, we extend AFA to scale space rendering, SSR, as a novel attention mechanism for multi-scale inference and be more robust toward gradient the issue. We treat the multi-scale predictions as samples in a scale space representation and then can express the scale attention as the volume rendering form. This scheme provides a hierarchical, coarse-to-fine way of combining predictions using a scale-specific attention mechanism. The choice of phi plays a role in determining the amount of gradient that flows through the predicted attention. Using absolute value function as our phi, SSR is more robust toward gradient vanishing problem. It leads that our SSR have better overall performance. Here is our overview method. We use AFA to replace the aggregation node in DLA network and use SSR to fuse multi-scale prediction to get the final results. On the Cityscapes benchmark, AFA DLA achieves the best performance on the validation set and competitive performance with the top performing method on the test set. Furthermore, AFA DLA uses much fewer operations and parameters when compared to top performing methods. On BDD100K benchmark, AFA DLA achieves the new state-of-the-art performance on both sets. On the boundary detection task, AFA DLA set the new state-of-the-art results on both datasets. The visualization of the attention maps shows that our AFA modules provide a more expressive way of combining features. The visualization results corroborate that SSR learns to focus on detailed regions in larger scale images and on lower frequency information in smaller scale ones. The qualitative comparison stands that AFA DLA can better distinguish object boundaries and correctly classify object classes. Thank you.